All right, guys. So yesterday we did some work in Basic 37. Okay. And do you guys have any questions? Do you have any questions? Okay. I'm going to jump to Basic 38. Basic 38. Hopefully that, well, I'm leaving, there's some of the rest questions for 37. Oh, I'm leaving all those questions for you. And you, if you have any questions, please don't hesitate to ask. Basic 38 is primarily about in the cases that we have the factors. Okay, you can see they're all given as factors. How do we sketch? How do we sketch? Okay, you're being asked for domain and range. I think range is going to be a hard question to answer. So if you don't get it right, if you don't get it easily, just leave it out. The primarily, we want you to be able to identify the X-intercept, okay, and have a sketch, okay? Take the first one, for example. Okay? The first one, we have f of x, right? So this is a function, of course, and it's a rule, right? We have four factors. So x plus 3, x plus 1, x minus 2, x minus 4. You can see once we have the factor form, well, this is also, you know, if you recall what we learned in factorization theorem or fundamental theorem of algebra, then you can tell that the x-intercepts can be told right away, and the y-intercept, you just plug in the numbers, right? So, so to sketch, okay, we can find the y-intercept, right? Y-intercept. For y-intercept, we just have to plug in x equals 0. 0. So this is 0, 0, 0, 0. Okay. And calculate, so we get 24. So that's where the curve crosses the y-axis. X-intercept, right? How about x-intercept? X-intercept, we're setting f of x equals 0. So this should be pretty familiar with you guys. So we just set the entire function, which is the output, equals to 0. And of course, using principle number 5, and we get x equals to -3 or -1, -1, 2, 4, right? So the x-intercepts there are 4 of them, right? One is a -3, 0. The other one is -1, 0, 2, 0, and 4, 0. So by this time, we already have all these intercepts, right? We already have these intercepts. So we can set up the rectangular system. Okay. And of course you can, in these days and time, you know, using graphing calculator, you don't have to do much, right? Just to identify the points. But what I want to indicate is that I'm showing you this graph, this setup is because, oops, okay. It's because I want to show you that it's a process. It's a process, right? So first you identify the y-intercept, right? The y-intercept is 0, 24, right? We can put that point in the graph. 0, 24. That's one dot. That's one dot. Let's see if it shows. Okay, it should be somewhere up, right? It's higher up there. So we need to adjust the view a little bit. I say I can make it 25, right? Just to make sure that point is included right there. Wait, how come that point doesn't show? I think wait. Let me choose, let me get that point. It's a point. I didn't make that selection. So that's the point. You see, that's the point right there. And that's the y-intercept. The x-intercept, you can put them in place. Okay, you can in places. So what do we see? Okay, so what we will see is that how the curve wiggles, right? The first one, let's put a red dot. Second one, third one, the last one. Okay, so these are the 4 dots, 4 x-intercepts. So to sketch the curve is pretty easy in the sense that we just need to figure out, is the curve going, because the curve is going to go wiggle like this, right? Either this way, right? Crossing here, sorry. Okay, so the curve either goes this way or the other way. We don't know which way. So how do we determine, right? Suppose we don't use a calculator. Suppose we don't use a calculator, or it goes the other way. Right? Because it has to go some way. So how do we determine that? Right? This is how we determine that. Okay? Because this polynomial has a degree 4. Okay, this polynomial has a degree of 4. As a degree 4 is x to the power 4. If you look at the leading coefficient, right, if you can multiply this out, the leading coefficient in this case, if you expand, it's going to be 1. It's going to be a positive number, x to the power 4. Okay, finding the leading coefficient is pretty straightforward, right? You just FOIL. The leading coefficient is a positive number, and it's a multiply x to the power 4. X to the power 4 is x to raise to the power of even number. So as x approaching positive infinity, or as x approaching negative infinity, and we can tell x raised to the power 4 is as a dominating term, is going to approach a positive infinity. So it's not going to be the green, it's going to be what? It's going to be the purple. This is going to be the curve. This is going to be the curve. So you can have some, I mean, remember, we only have computers and technology available in the recent, I would say, since 1940s. Okay, since 1940s, since last century, less than 100 years, okay? Say about 80 some years. So in order to, well, to graph these functions, it has been, has been quite some time in history. So before the technology, people would figure it out this way. Or in the case, well, hold on a second. This curve has to pass that point. Okay, so let me show you a better sketch. Okay, let me show you a better sketch. Okay, trust me, maybe I can do a little bit better, right? So this goes, this to me is a sketch. Okay, it has to pass the y-intercept. Okay, so in both directions, it goes to infinity indefinitely. And of course, this is just a sketch. This is just a sketch, right? So before you touch that screen, okay, start touch the calculator, whatever tool you have, you already have some idea about how the curve may look like. Okay, from some of the basic knowledge. So without further ado, let's complete this question, right? We're going to graph this function, and you will see if our assessment before the graphing is close. There you go, right? There you go. So that's the curve. Of course, there's certain pieces cutting off, and we just have to make some adjustment. We just have to make some adjustment. Okay, so maybe negative 30, something like that. Okay, it looks like it goes even higher, so I'm going to make it like 40-ish. So that's the curve. So our assessment is about right. On these two ends, those are the cases. Those are the cases when this is the case when x is approaching, when x approaches negative infinity. And these are the cases when x is approaching positive infinity. And we just talk about leading coefficient, right? In both cases, x raised to the power 4, in either case, in both cases, approaches positive infinity. That's why the curve goes up on both sides. Okay, you see number 3, you have 3 terms, right? So I'm going to leave the rest for you to play. The range, however, okay, just don't worry about the range. Okay, basic 38, don't worry about the range, because for the range, it's hard to find the accurate number here. And you will be able to find it easily when you're in calculus class, okay, using the derivative tools. Okay, so let's not dwell on these. Okay, now 39A. 39A is about factoring polynomials completely. So still, we have our eyes on the series. Okay, every polynomial we have here can be factored, every one of them. Okay, every single one of them can be factored. It just, oh, but wait a minute, I think I'm gonna make a change, right? This change was meant to be made before. 39A. Okay, I was planning to give you more exercise, but then I didn't do it. Question number 1. Okay, let's start with number 1. Question number 2. Okay, please make a change on your end. Okay, it will be too difficult to factor as the way that was given. So minus 5x squared plus 4. Okay, so could you guys change your question on number 2 to 5 times x squared instead of 5 times x? Okay. The only additional step you need to do is to, maybe we just do number 2 then, right? We just do number 2 then. Okay, let's do number 2 then. Okay. For number 2, and you can see this is actually a quadratic. This is actually a quadratic. Why is that a quadratic? Because if you see that as x squared,
you change it to u, right?
That's right. That's right. times 5x squared plus 4, right? So you have a u, right? You're right, this is a u. If you see it that way, and this is the factoring of quadratic. I mean, for academic applications, right? You guys are in academics right now. Quadratic, just one of those functions, just show up over and over again. For for reasons, for its simplicity or whatever, it just show up. It just show up in a lot of places. Okay, so continue the factoring, then we're going to get x plus 1, x minus 1, x plus 2, x minus 2, right? Then you can continue to do what we did, and then the rest is similar to basic 38. Okay, I'm gonna leave these for you guys, okay? Because we're gonna move forward. Okay, 39, that's 39A, 39B, and 39C. You guys see that? The next pages, the next 2 pages, you have 39B, 39C. Some of these exercises in 39, 39B, 39C will be something closer to what you're going to see in calculus. Okay, you're going to see more of those in calculus classes. So try to simplify those. Okay. The other issues I want to just to remind you of, you should know how to do long division. Okay, you should know how to do long division. You will need that in Calc 2. Okay. And I'm going to quickly mention something here, which is called Basic 40A. Okay, this title is called partial fraction. What is partial fraction? Partial fraction. Partial fraction is a technique you are going to use in Calc 2. Okay. I don't plan to spend a lot of time in here to do it, because at the time your professor will do it. But I will give you some basic ideas. There's general 4 cases. Okay. In the simplest case, the partial fraction basically is an idea. For example, if we have x minus 3, say minus 1 over x plus 2, right? We know how to handle this case, don't we? It's just an example, Okay. How do we handle this case? This is a statement, this is an expression, right? You will normally do finding the common denominator. And that's one factor in the denominator, and there's another one which is x plus 2. With the common denominator in place, okay, and over here you're going to have x plus 2, you're going to here have x minus 3, right? This is something you have learned in algebra, didn't you? Of course, you guys learned that in algebra class. You learned that in algebra class. So now you're going to take this numerator, subtract this numerator. So you're going to have a 5. Okay. Partial fraction. Okay. Let me go with here, which is much easier to handle. Okay. In algebra class, that's what you learn, right? You do this. In partial fraction, in calculus class, in Calc 2, what do you need? You might be given something like this. And then you're going to break it to pieces. This process, okay, reverse the process. It's backward. You guys see that? Do you see that backward? That's called partial fraction. You have one fraction and make it into two other fractions. Why do we do that? Because after that you can integrate. It's a necessary technique for integrating some functions, such as this. Okay, we know this is called a rational function, right? In your calculus class, you probably will be asked to, hey, integrate this for me, right? Integration. Integrate. What do you do? What would you do is it could be definite integral or indefinite integral. Then you will be using this relationship. You reverse it. Okay, you'll be learning a technique to do this. Okay, I don't plan to go over this technique in this class because taking Calc 2 is 2 semesters away, right? 2 semesters away. So by that time, whatever we do here, you might have forgotten. So if you get the idea, it's not a big deal. You'll get it. So these two, if you do this, and you answer, if you break it out, if you break it up, okay. So one fraction turn into multiple other smaller fractions, especially with linear factors. And then your answer will come handy, which is something like this. Absolute value of x minus 3 minus absolute value of x plus 2. Something like that, and plus a constant. Okay, that's the reason we do this partial fraction. Okay, so basic 40A, I have 40A, 40B, 40C, 40D, 40E, and these are different types. These are different types of situations. We don't have time to go over them, but once you get into calculus class, it's a simple technique will teach you how to do this. And so, yeah, we're not going to do that in this class, but I give you this idea. Okay, continue. Okay, 41 ABC, and these are about finding compositional functions, adding, subtracting, multiplying, dividing. Not very strange to you. Finding inverse. Okay, so let's spend a little bit of time on 42A. Okay, finding the inverse. Basic 42A. Okay, this one is just the idea. Okay, see, I give you the idea, but not the method, right? And you're gonna learn that. Your Calc 2 teacher will teach you that. Okay, all right. Be sure you know how to do long division, okay? But be sure you know how to do long division. So let's get to 42A. Okay, 42A. For 42A, it's to find inverse. And we know that only one-to-one function has inverse, right? Only one-to-one function has inverse. And to find inverse, there's a general procedure. Okay. I'm going to use number 2 as an example. As an example, f of x equals to x squared. This function doesn't have inverse, right? This function doesn't have inverse. But if we have a restriction, but if we require x is less than 0, it does. Okay? Because we just use the piece on the left. We'll use the piece on the left. Okay? Do you follow me? Okay, so find the inverse. Now, how do we find the inverse? The general step of finding inverse is that to see if this will help you recall that we're going to have a y equals to x squared. Okay, and then we're going to swap x and y. Remember seeing this? Swap. Swapping, the consequence of swapping is this. Y turn into x, x turn to y. And then solve for y. Okay, so these are the general, I would say it's not even 3 steps, just 2 steps. Swapping and solving. Swapping and solving. Okay. So solving for y, what do we get for y? Right?
Square root x.
Square root of x. But be careful. Okay. Along the way, there are a couple of things I want to point out. Very good. Okay. If we take square root on both sides, okay, if we take square root on both sides, okay, you're right. You're absolutely right. Okay. Let's see what we get. Let's see what we get. Okay. So let's finish this one. Okay. Square root of x. Okay. Square root of x equals to the absolute value of y. Okay. We need to drop the absolute value. How do we drop the absolute value? Because what do we get? What we are getting should be a 1-to-1 function. It shouldn't have a plus minus. Okay. If you get something like this, that's wrong, because you cannot have, your final answer has to be a 1-to-1 function. Okay, so when you get, if you get to this point, you will be considered either incomplete or incorrect. Okay. So now, so you have to choose one. You have to choose one. How do we choose that one? So let me show you how to analyze this. How to analyze this. When we are dealing with functions, we always must be aware of the domain and range. Let me say it again. When we are dealing with functions, we must be always aware of domain and range. In this case, the given function, the domain is specified. The domain is specified. The domain is specified. What is a domain? We are told the domain is x less than 0. And what is the range as a result? What is the range? You square a negative number, it's going to be positive, right? Right? So x squared is going to be positive. Okay? Because the domain is x less than 0. 0 is not included. Therefore, the range for this function is positive. And when we swap when we swap, what happened? Not only the symbols are swapped, domain and range also are swapped. You follow me? Because now we're heading to find the inverse. So if this is the domain for f, okay, this is domain for f of x, right? At this point of swapping here, at this point of swapping, the inverse function's domain and range is also determined. You follow me? So the significance of the swapping is not about only symbols, it's about the swapping on domain and range. All right, so now the x is a domain. In this case, it's going to be this guy. Okay, so it's going to be x larger than 0. And the range, okay, the range is going to be x less than 0. Do you guys see that? Remember, the swapping will cause the domain and range. Remember, the function and its inverse, if a function has inverse, its domain is always one's domain is the other's range. Always, always. Okay, so this swap is the moment that the switching of domain happens. Okay, the domain for f, and this is domain and range for its inverse, and this tells us the range for y is going to be negative. I'm sorry, this is I'm sorry that I put this in the wrong place. Okay, the y. Okay, the y. Okay. Now, so this y has to be negative, and therefore the answer here should be a negative. You get it? So this is the process. It's not simply just a switching of symbols. It also switching of domain and range. And it is at this moment, the domain and range of the inverse functions is also decided. Got it? That's very important to understand. That's very important to understand. So now we have the inverse function. We have the inverse function. That inverse function is negative of root x. Okay, and of course its domain and range are here. Has been determined. It has been determined. All right, so with that said and done, okay, we're going to pass some functions. Let's look at number 8. Okay, we're going to do number 8 and number 9. Okay, I'll leave the rest for you. Number 8 and number 9. F of x is equals to e to the power 5x plus 4. Of course, first you're going to decide, hey, is this function 1-to-1? We have to decide that, right? Only 1-to-1 function has inverse. Well, then we're certain that this function indeed is 1-to-1, right? You can do graph and whatever. So let's do the graph. Let's do the graph. Okay. The graph. You can plot some points, whatever. Okay. So suppose I have a obviously there's a lot of shift to the left, right? Which is expected, so let me just, with the convenience of modern technology, and of course you can quickly decide whether this one has inverse or not, right? It passes both the vertical line test and the horizontal line test, right? So it's a one-to-one function. It is one-to-one function. This curve actually looks very strange, but it's okay. Okay, we'll deal with it, right? And it will never touch the x-axis. It just get infinitely close, right? But this picture, it just, it shows us it's a one-to-one function. So we have decided on that. Okay, so I'll make it just a little bit shorter. This is good. Okay, but you can see the domain. This function's domain and range is naturally decided. It's naturally decided. Okay, so domain, what is a domain? All real numbers, right? All real numbers. All real numbers. And what's the range? Well, e to the power of anything is always positive, right? Larger than 0. So the range is positive, all positive numbers. Okay? Now, let's proceed to find the inverse. Let's proceed to find the inverse. Proceeding to find the inverse, and of course, we're going to assume this is y. Okay, and swapping. Swapping x and y. Okay, we know the domain and range for the given function. Okay, let me put this on the top because it just put it here, so that way we can have a better view. Okay, all right. So when we swap, we need to take care of two things. Okay, one is a domain and range, and the other one the range for the inverse function. So this is going to be e raised to the power 5 times y plus 4. At the same time, okay, the domain and range of the inverse, it's also decided right here. And what will be the domain? The domain is x is larger than 0. Okay, the output was larger than 0. Now the input must be larger than 0 for the inverse function. And what's the range? The range would be whatever in the domain, all real numbers. So domain and range is determined at this point for the inverse function, And then we're solving for y. Okay, this step is very, very important, and it's very, very important to understand. It is so, okay? Now we're solving for y. How do we solve for y here? Okay, now x is a positive, right? This x is a positive, so we can take a natural logarithm on both sides, right? We can take a natural logarithm on both sides. So we'll have ln x equals to ln e to the power of 5y plus 4. You see here, when we take a natural logarithm, we know that the domain for natural logarithm are positive numbers. So this has to be guaranteed to be positive. Otherwise, we cannot take that natural logarithm. So being aware of this process is absolutely critical. It's absolutely critical. Okay, and of course, the rest is straightforward. Okay, so we have ln x equals to 5y plus 4, and solving for y is equals to 1/5 multiply ln x minus 4. Right, so that's the inverse function. That's the inverse function. And the final step, you're going to write it as f of inverse of x is equals to 1/5 times ln x minus 4. So finally, let's look at the picture. Let's look at the picture, right? We have this picture over here, and we're going to graph it. We're going to graph the same function. I'm sorry, we're going to graph the inverse function in the same picture. Red, it doesn't show, okay, because I need to adjust the I need to adjust the 8. Does it show? There. Okay, so let me make some more adjustment. Because we want the scales look alike. Okay, so maybe this is a -5, and that's 8. Is that better? So now the 2 and 2 is about the same length. Is it still symmetrical with respect to that magical line of green? Is it? It still is, and it must be. It still is and must be. And it still is, must be, and all the properties about inverse function, they must be satisfied, including domain and range relationship. One's domain is the other's range, and vice versa. Okay? So one other properties about inverse function I wish to go over with you here. Okay. An important property we must go over here is that we're going to take this case as our example. Okay, this is our inverse. Okay, and the function, the given function was here. We know graphically it satisfies the relationship, right? It satisfies all we required. But there's another relationship we haven't emphasized enough, but it's very much needed, and it's very, very important. Okay. I know for sure you're going to see it in Cal. Okay, is f of inverse composite f of x is equals to x. We have seen similar properties before, though. Okay, so I'm going to take this opportunity to review with you some of the related ideas. I believe we talked about this before, didn't we? In trigonometry. Did we?
Yeah.
But we will recall this. Okay, we will. I will review that part with you today. Okay. It's about this property. It's about this property. Okay. this property is also universal for all pairs of inverse functions, all function and its inverse, okay? It's always true. However, we need to understand which one is in domain, which one is in which domain, okay? Which one is in whose domain? Okay, that's important, right? Even though they're both axes, they're not always the same, as we indicated in the trigonometry. Okay, today we're going to review that part as well. So now I'm going to put the domain for the inverse. Okay, just make it close to us. And the domain and range for this guy. Okay, we just want to put them together. So these two properties is universal for any pair of inverse functions to each other. Okay. So first we're going to check this, that is true for our situation. That is true for our situation. But before we check that, we need to understand how this works. Okay, how this works. Okay. So for f of inverse, f of x, the input x, the input x is from the domain of f first. Remember we talked about that in trigonometry, right? Trig and trig inverse. And this will be given to f. The output is f of x. And this output will be given to the next one, f inverse. Okay, it produces, it's going to be this guy. It produces f of inverse of f of x. And it is going to be the same as this input. Okay. On this other one, however, this x, even though they're both called x, they may not be the same. Okay. We're going to review trigonometry. You're going to see that even better. Okay. Now, x is from the domain of f inverse. Okay. So f inverse is the first rule applied to x, because this x is from the domain of f inverse. And then it produces f inverse of x. Okay, and this output is going to be given to the f. That rule applies to it, and it produces f of inverse of x. That is going to be equals to x. So this x is from the domain of f inverse, and this other x is from the domain of f. Okay, all right. Okay, so these two x's, even though they're addressed with the same symbol, they are merely placeholder. They may not be they may be totally different. Okay, recall. Let's see, what do we recall? Okay, I believe it's a trig either 6a or 7a. Okay, but I'm going to just give you I'm not going to use a number because I'm not sure about the numbers. One is a sine of sine x equals to x, and there's a condition right? There's a condition. Has to be less than or equals to 1, right? And the other identity is arc sine of sine equals to x. Under a condition that the x has to be less than or equals to pi over 2. Right? This is a typical example. These two axes may not be the same. We addressed this before, right? But now we're refreshing this. Because sometimes the domain and range after this, domain and range are different after all. Okay, the domain and range are different after all. So in this situation, what does it say? Right? What does it say? If I choose a number x from the domain of arcsine, the domain of arcsine is less than or equals to 1. The absolute value is between -1 and 1. So that number is a ratio. This x is a ratio from the domain of arcsine. That's a ratio. It will be regarded as a ratio. And that ratio has to be between -1 and +1. Okay, and then given to arcsine, okay, and it produces, of course, arcsine, and this is an angle. Okay, this is an angle. This angle is going to be between -pi/2 to pi/2. And then we supply this to the next function. Okay, we supply this as the input for next function. So the sine of this angle. Remember, this is an angle. Okay, this is a ratio. Okay, angle. And now we take this angle, and this angle is between -pi/2 to pi/2. It produces a ratio. Okay, and that ratio is going to be exactly the same as the input. Okay, in the second case, this x is going to be between -pi/2 to pi/2. Okay, -pi/2 to pi/2. If it's from there, okay, so it's an angle. So this is a ratio. This is an angle. Do you guys see that? This is a ratio. This is an angle. So even though they're both called x, but they're different. Okay, they're different. You have to see what is the function that works on it. Okay. Okay. So then the first function will be sine. Okay. But this angle is from here because we know that arcsine has its specific domain. Its inverse is a restrained sine, right? It's a sine between -pi/2 to pi/2. And next, so this is an angle. Sine x, take this angle, it produces a ratio, and that ratio is sine x. When you see sine x, you should think of ratio. Sine x is a ratio. It's the opposite over hypotenuse. It's a ratio. Sine x is a ratio. Cosine x is a ratio. Tangent x is a ratio. And so on and so forth. You guys got me? Okay. And this ratio, which is surely between -1 and 1, and then we apply it on the arcsine. Okay, we apply the arcsine rule. Okay, the arcsine rule, of course, is applied to the ratio. This is a ratio. And of course, arcsine is going to produce angle. And this angle is going to be exactly the same as the input angle. okay? You can see the consistency here. The functions are inverse to each other because in this story, okay, these two functions, okay, the function f, okay, function f, I call it arc sine, doesn't matter, right? Its inverse is sine with restrictions, which is the absolute value of x less than equals to pi over 2. Okay, so if you have any questions, feel free to ask me, but I will direct you to, to the lectures we did before. Okay, but any questions, so please bring them on, okay? But here, I'm not going into the details because we did cover them then. The reason I bring this up here is because I want you to see the consistency here. It doesn't matter what function you're talking about. Inverse functions, as long as two functions are inverse to each other, okay? As long as the functions are inverse to each other, they all satisfy this relationship. All of them, no exception, no exception. So now let's verify this is true for the two functions we just have worked on at hand. Okay, so that was a review. So let's see if this will be, so get your paper, pencil ready and work with me. Okay, get your paper, pen, pencil and work with me. So now we're gonna work this guy. Okay, we're gonna verify. It must, because if it doesn't, it's wrong, something was wrong, okay? So f inverse of f of x. This x here, because it's so close to f, therefore this x is from the domain of f. You follow me? This x is from the domain of f. What is the domain of f? All real numbers. You follow me? This x is from the domain of f. We must be aware of where it is from. And next, okay, so we have f inverse. Now f of x, what is f of x? F of x is this guy, right? F of x is this guy. And f inverse, what is f inverse? F inverse is this guy, right? And the x is here. Now the x is e to the power 5x minus 4. So 1/5, this rule will apply with the x replaced by that guy. You follow me? With that substitution, if this were x, that was x, because that's the rule of the function. Now this x is changed to e to the power 5x plus 4, and this x will change to e to the power x 5x plus 4. Do you guys follow? And then we simplify. Okay, then we simplify. Okay, 1/5 ln of e to the power 5x plus 4, and this piece is just equals to 5x plus 4. Okay, 4 minus 4 is 0. So in the end, what do we get?
X.
That's right. So this piece is verified. And we also need to verify the other piece. We also need to verify the other piece. Okay. The other piece is this piece. Okay. And this piece, the X is so close to F inverse. So this X is from the domain of F inverse. So as a result, this X has to be positive. You guys see that? Okay, so that's equals to F of F inverse of X, where X must be greater than 0, because this X is from the domain of F inverse, and domain of F inverse is X larger than 0. Okay, you can see that all these must match perfectly. Otherwise, you wouldn't be able to carry out the domain. Okay, so now, what is F inverse? F inverse is this guy. Right? This is a positive guarantee. This is meaningful. Right? This is meaningful. And next, what is F? What is F? F is E, right? F is the E to the power of something, right? E to the power of some stuff. E to the power of 5x plus 4, right? If this were X, if this were X, right? If this were X, right? That's how f of X is defined. And now this X is this guy. Therefore, this X will be replaced by it. Did you see that replacement? I wanted to show you that on purpose. Did you see that substitution? Should I do it again? 5x plus 4. Okay, so this guy, if this were X, that's the rule of the function. So when this X is replaced by that, and this X will also be replaced by it, by the same thing. Is that clear to you? Okay. Symbolic operations. Okay. Now we have e to the power of, so we're going to simplify the power. We're going to simplify the power. In the power, 5 times 1/5, that's equals to 1. So we have ln x minus 4 plus 4. Equals to e to the power of what? Ln x. E to the power ln x is equals to what? What does that equal to?
X.
That's right. That's right. Okay, so you can see it's verified. Verified. So all pairs of inverse functions, they must satisfy the domain and range. Okay, one's domain, the other's range, vice versa, and also these two properties. Okay, and then of course, I should specify this guy is in the domain of F, right? And this guy should be X is in the domain of F inverse, just to make it more specific. Okay, so let's take a break. Let's take a break, come back at 9:16. Okay, so let's take a break. Sorry, I'm late. Okay. So shall we work on number 10, right? Number 10. The other functions, I'll leave them for you because I think you'll be okay with it, but unless you have questions, so please don't hesitate to ask me, okay? The primary things that we want to understand is the general ideas about function, and function has inverse and these important properties. In particular, these two. Okay, in particular, these two. And we have seen that in trigonometry, now it's in exponential and logarithm, right? And they have these universal properties. They have these universal properties. So let's look at number 10. Do you guys want to take the lead to do number 10? Yeah? Your turn. You are taking the lead. If any one of you would like to submit your work, I would love to see it. I would love to see it. Oh, great. Thank you, Bailey. I will take a multiple work even for the same question, okay? Let's see. I'm gonna download. Okay. Do you see that? Do you guys see this? Okay. So he wrote down the function, right? And be aware of the domain, and he swapped and he solved for y, which is ln y minus 5 equals to, let's see. We have, did you add 5 on both sides?
Yeah.
I don't think we can do that. We need to treat this piece as one piece. Okay, so we cannot do this. We cannot do this. We cannot add 5 and take away the 5 and add the 5 to the other side. What should be done is this. Okay, it should be y minus 5 equals to e to the power x. By definition. And then y would equal to e to the power x plus 5. You know what I mean? Okay. So we need to treat this parentheses as one entity. It's the omega. Okay. But very good try. And so let me go back to our previous screen, and I'm going to go over this. Whoops. Resuming share. Okay. So here he did this. He did the swap very good. Okay. So we have the swap. Y minus 5. Okay. And here we need to be aware the swap will cause the domain for the inverse function. It's already decided. The domain would be all real numbers. Okay. And the range is also set. Okay. So this y is going to be larger than 5. Okay, larger than 5. So in overall, it just has to guarantee that the domain and range would make it, everything is just right. Everything just right. And everything we operate is in the domain and range. Okay. So now what we do here is that refer to the definition. Okay. So we have a situation here. A logarithm definition says this. Okay. I want to remind you guys to always be aware of the definition of logarithm. Okay. And this if and only if b raised to the power of the triangle is equals to omega. When we have y minus 5, this entirety is omega. Okay, our base is E. So this is ln. So quantity at the omega place is y minus 5. And so this quantity is y minus 5. Okay, the quantity at the place of triangle is x. So this is x. So this is x. You can see that how that works? Okay. When working with logarithm, always remember definition. Always refer to the definition. Okay, so you will never be lost. You'll never be lost. So we just take this piece over here. We really just take this piece over here. Okay, you can work this out on a scratch paper or whatever, right? And you don't need the parentheses here. And then you solve for y. Okay, so this is the piece we're solving for y. Solving for y. Okay, solving for y. And y, of course, equals to e to the power x minus 5. So this is the e to the power x shifting down by 5 units. So let's look at the graph. Let's look at the graph. Okay, this graph, so let me put f of inverse here. Okay, that's e to the power x minus 5, right? We know how to do this graph, right? ln x shifted to the right by 5 units, and e to the power x shifting down by 5 units. And you graph these two and you sketch these two in one picture, right? So this picture will give us just shifting down by 5 units, shifting down by 5 units. This will be 38. I will make some adjustment, okay, here. This is probably -8. That's going to be better. Okay, so this is e to the power x. E to the power x, you know, it's over here, right? So I'm not going to draw that. And the next one is going to be ln x minus 5, right? ln x minus 5. So we're graphing the other one. This is ln x is shifted right by 5 units. Okay, so make it red there. Okay, and horizontal asymptote, vertical asymptote, be aware of them. Be aware of them. We'll get to them. And let's see. Okay, so let me make the view. So let's make 12. All right. Did I make a mistake somewhere? It should be +5, isn't it?
Yeah,
right?
+5.
It should be +5.
Yeah.
So this should be +5. Because I was thinking that's gonna be not gonna be symmetrical along that green line, right? See? Okay, so e to the power x +5. There. That's about right. That's about right. Okay. So you can see that, you know, looking at different perspective, it helps us to check, right? I made the dumbest mistake. But it can be found out, right? In the process. Did I make that same mistake yesterday? Probably with my other class. Okay, so I'm gonna just make some more adjustment to the picture. Okay, and it should be symmetrical with respect to that magical green line. Right? And then you can observe the intercepts, x-intercept, y-intercept, asymptotes, and so on and so forth. Okay? So I'm going to leave you guys at this point because there's so many other questions you could ask by studying thoroughly. And you can also verify. I'm leaving the verifying part. Okay? I'm leaving this verifying part for you. Okay? I want you to verify these two. How about you guys do it in class? Would you like to do that? Please do this in class. Okay, so I can check your work. Now this is repeats. Okay, so for this, for the pair of function we have here, right? F of x, F inverse. When you verify, if I made a mistake, say if I had e minus 5, e to the power x minus 5, in the verification process, we will discover something is going to be wrong. Okay. Okay, verify, please. Okay, I want to check your work. I will be giving you another written quiz, okay, this week, how to find the inverse, okay, and indicating their domain and range, and maybe some other questions. Okay, so you had a one written quiz, you're gonna have another one. Hold on a second, I'll be right back, okay? See anybody submitted some work? Very fine. I mainly want to show you, I want to see your steps. Thank you, Bailey. There. Okay, here. So he's working on f of x, right? F of x is, I forgot, what is f of x? F of x is ln x minus 5. Okay. To change the screen, it covers my previous screen. I have to. Okay. F of x is ln e to the power x minus 5. The other one's ex minus 5. Okay, got it. Go back to the previous screen, right? You have e to the power of so f of x, that's ln, and that's good. And ln, f is ln, right? So e to the power x, all of that. Yeah, what do you think? It's good. It's good. Okay, so that's how you verify. I especially like that he start from one side. Okay, he start from one side because the question is asking you to verify. You must start from one side. Okay, it's like proof. You don't know is it true or not. Okay, you need to pretend it's not true yet. It should be true. But you need to pretend it's not true yet because along the way, we might identify certain thing is not working. For example, if I had to use e to the power x minus 5, I would be in trouble, right? I made a mistake. So this process allows us to also examine our work. Okay, all right, so that's a very good work. And for the remainder of the time, okay, for the remainder of the time, I wish to get started on something else. Okay, I'll start it on something else. So where's my, okay, my previous screen. Okay, let's go back to our previous screen here. Okay, so that part. Do you want me to show the work, or you're okay with it? Okay, I would just, it was the work I will be showing is going to be similar, but I do want to get started on another section. And this other section is directly related to your calc. Okay, so F inverse, let me just quickly get this done. Okay, f of x, just put it there. And e to the power of this guy plus 5. And that's going to be x minus 5 plus 5. And last but not least, so the it works like along that way. Okay, and the other piece, Mine is slightly different from Bailey's because I was just doing all the detailed steps. Okay. He combined steps, which is fine. So f of inverse, so that's e to the power x plus 5. And then we have ln of e to the power of x minus 5. Okay, so that's going to be equals to x. Okay, so that's verified. All right, the next session I wish to go over with you. We're going pretty fast today, okay? We're going pretty fast today. This is it's a basic 43A. Let's see if I have used the same number in my new edition. Okay, 43A. Yep, same number, 43A. Basics 43A. You may not see this kind of exercise a lot in a lot of the in your algebra classes or in your pre-calculus classes. Okay. I created these questions using a lot of the exercises directly from your calculus textbook in response to the tremendous difficulty I personally observed for students who were taking calculus classes with me when we were covering chain rule. Okay, chain rule is something you are going to learn in calculus class. So we're doing these exercises to prepare us for the use of chain rule. Is that clear? So this is the algebra part. So what we did earlier, what we just did, okay, is about compositional functions, right? Composition of functions. You guys did pretty well. You guys did pretty well. Okay. What it does is that f composite g, you guys are pretty familiar with this, right? It's f of g of x. So this composition is going from, you know, given, right? Given f, given g. If you're given f and given g and you know how to compose it, right? You know how to compose it. However, in your calculus class, you need to decompose it. You get it? So now what you learned, so far what you have learned is that you learned given f and g, you're going this way. In your calculus class, you need to be able to do it the other way. Explicitly or implicitly, you need to know what you're doing. In other words, that you are given a function which is already composed, and you need to break it into pieces. You need to decompose it. Do you follow me? Okay, let me give you an example. Okay, and I found there are not a lot of exercise to do the decomposition. I took the liberty to assume, that that is because our student didn't do enough exercise of decomposing. Okay, you may not be able to find a lot of exercise in the summer textbook. I hope that this exercise will compensate for that. Okay, so I'm going to show you what it is. Okay, so I will call this decomposition. Decomposition. Okay, this word is created entirely by me. Okay, because I haven't seen such a word being used in other places. Okay, so I'm going to explain to you. The decomposition is from the already decomposed function and to discover, okay, to discover f and g. All right, so I have, I hope I have clarified what is the intention. Okay, so the decomposition is the opposite of a composition in this regard. Okay, first example. Okay, first example, √3 of 1 plus 4x. Most of these exercises I have given you here, including 43A, 43B, I would say 99% of them are from your calculus textbook. Okay, so I want you to practice, so you'll be ready. So you will not have that tremendous difficulties when you are learning chain rules and applying chain rules. I hope. Okay, so this function is actually already composed. Okay, so you have this form. So you're gonna break it down into two basic functions. Remember basic functions we talk about? Basic one, that table, basic one, right? So now you probably see how I designed the whole thing. Okay, how I designed the whole thing. My handout is that I always want to refer back to basic one. So let's see how we decompose it. I'm going to give you an example. It's very easy to do. I want to, don't get stressed out, okay? It's very easy to do. Okay, so what you see here is that what you do is that you say, okay, this is a cubic root of this guy, right? And how would I make it simple? You gotta make it u, right? And what will be u? U is 1 plus x. Do you guys see how that's been done? And this is linear, and you know, the derivative can be found easily. Okay, so now let's discover what is our f, what is our g. Okay, what is our f, what is our g? Your g is going to be 1 plus x. Your f is going to be the √3 of x. So that's how you decompose. Okay, that's how you decompose. And of course, you're going to verify. Does it work? Does it work? So what you're going to do is you're going to verify, you're going to do f composite g of x equals to f of g of x. That's this guy, right? G of x. Okay. And then you have your f, you have your g is 1 plus 4x. And then now you can apply your f, which is cubic root of what? 1 plus 4x. This process is called decomposition. Do you follow me? Did you see that can be done? Did you see how that's done? Decomposition. okay? And you need to know you need to know how to do the decomposition when you learn chain rule in chapter 3 of calculus 1. A lot of our students, when they were doing chain rule in chapter 3, oh my God, they make all the kind of mistakes. Okay, I hope this helps. Okay, shall we try another one? Number 2. Okay, we have 2x raised to the power 3 plus 5 raised to the power 4. The general principle of decomposition is that you should be able to decompose your functions into bits and pieces like those you saw in basic 1 table. Want me to repeat that? The general principle of decomposing is that you should be able to decompose your functions into pieces that we have seen in table basic 1. Okay, so one category is polynomial, right? One category polynomial. We can easily find the derivative of polynomial. So you want to decompose into polynomials when you can, or root functions, or sine functions, or cosine functions alone. Okay, and then you will see the magic of chain rule done when you're in calculus class. Okay, so I would appreciate you guys come back to tell me how these exercises have helped you after you've taken Calc 1. If you would, I would appreciate it because I like to have some feedback on it. And I created these exercises, and these exercises are not available in a lot of other places. So I would like to have some feedback, okay? But if you don't, it's okay, no big deal, okay? It's just your feedback will be much appreciated. For example, in this case, right? If you expand it, that's going to be a lot of work, right? That's going to be a lot of work. So what you can do, you would compose it, say, hey, I'm going to make it simple. So how do I make it simple? How about I make this U? I make this guy U. How about that? This is my U. So my U is what? U is what? U is this guy. So this is a simple function, and this is a simple function. That's all you do. Really, the idea is very simple. Do you guys see that? And this is going to be your G. And this is going to be your F. And just remove the U. You can use U. It really doesn't matter, really. You can use U, right? But you can use in X. Because conventionally we use X, but it doesn't really matter, right? So that's you find F and G. And you should verify. I always encourage you guys to verify. How much time do we have? Oh, I will have reached the end of the class. Okay, so we'll continue to do more of these next week. Okay, so if you have a copy of a textbook, you open up your calculus textbook, right? If you have it, open up look for the section of chain rule. You're going to see a lot of these exercises there, but they ask you to take a derivative. So let me finish this by verifying. Okay, you should always verify. Okay, so F composite G. F equals to F composite G of X. Oops, sorry. Equals to, okay, equals to, oops, f of g, this is g, right? And f power 4. So whatever to the power 4. You see, it works, right? So you need to be able to identify those f and g. You got it? So if you're interested in, or you have time, I would encourage you to move forward. Okay, a lot of these exercises, and I even have some 43B. And I promise you 99% of them are from your calculus textbook. Okay, and what I hope I can give you a little just head start. All right. So keep on working. Okay, I'm really pleased with your work, and expect another quiz, written one. Okay, this might be one of those last, maybe I don't know, maybe another one, a written quiz for working out the inverse functions, specifying domain and range, and verifying that property. Okay, so that's going to be your second quiz for this week. And I will see you guys on Monday. If not sooner, I'll be heading to the office hours, and I will see you Monday. Have a great
All right,
week.
have a good one.
I'm sorry?
Have a good one.
You too. Thank you.
Thank you.
Thank you, guys. Very good work. Keep it up. We're getting there. We're getting there, okay?